Well, this is chapter 10, Area, Moment of Inertia. Today we're going to talk about deflection. Now, if you had a cantilever beam here and you push down on it on this side, you might expect that it would deflect a little bit. So this is a picture of the table in the Mechanics of Materials book, and it gives a deflection here as a function of the load, P, the length, L. E is a measure of the material. It's a property of the material, whether it's aluminum, steel, wood, or plastic, will have a different value of E, and that's called Young's modulus, or the modulus of elasticity. It's basically how much a particular material might bend under a given load. The last thing is I, which is called the moment of inertia, and that's a measure of the shape. So if we look back again at a different part of the book, you can see that here's some I-beam. Here's an I-beam standard shape, and there's lots of different dimensions that might be available if you were to try to buy a beam. And they have lots of different values of moment of inertia, which are pre-computed for you. So anyway, what we're going to talk about is what does this number mean? It's more of a relative term for us in our understanding right now rather than the absolute value. The units are inches to the fourth, which again, just in terms of absolute value and absolute meaning, it doesn't really mean much to us or help us much, but we can compare one shape to another and get a relative understanding of what moment of inertia might mean. Well, the moment of inertia is defined by the integral of y squared dA. If we had a couple of random shapes, we could find the moment of inertia about those. We're going to focus more on standard shapes in this course. And we just want you to know that the moment of inertia is a measure of the stiffness of the shape. It's a property of both the shape and the orientation. And the concept of inertia, we may have some experience with, but I kind of think of inertia as some sort of resistance to something. So in other words, if you were trying to push something, mass would resist its acceleration. The greater the mass, the smaller the acceleration for a given force. Mass moment of inertia resists angular acceleration. Polar moment of inertia resists twisting deflection, which we're going to talk about in mechanics of materials, and the area moment of inertia resists bending deflection. Again, we'll visit much more about that in mechanics of materials, but you should know that it provides stiffness and strength to beams and structures. Let's talk about how we can define it for a rectangle. Now, a rectangle has a shape of base times height. And I want to find it about an axis. So I'm just going to draw an axis here, right down the middle. I want to find out the area moment of inertia about that axis. Let's say that this is negative h over 2, and this is positive h over 2. And I want to just define a little differential element dy. Okay, so I have my formula here. I about x prime is equal to the integral of y squared dA. And I want to integrate that from minus h over 2 to positive h over 2. Now what is my dA? My dA is equal to b, which is the base, times dy. And I know that, and the base here is a constant, so I can just factor that out. So that's going to be b. And then integrating y squared, I get y cubed over 3. And I want to evaluate that from minus h over 2 to positive h over 2. Y here being the variable. So when I plug those in and evaluate that, I get the moment of inertia about that axis is equal to bh cubed over 12. Now that is a takeaway expression. bh cubed over 12 is the expression for the area moment of inertia of a rectangle about its centroidal axis. And we're going to talk about the centroidal axis in just a little bit. Well, let's compare a common shape in two different orientations and see if we can come up with some relative understanding of how moment of inertia plays into deflection. So let's say that this is a plastic ruler, and I'm going to push down on it on this, it's in this flat orientation. I'm going to push down on it with a force here. If this is being clamped by your hand over here, and if you push down, you'd expect that it might have a bend in it and have some significant deflection. However, if you were to orient it like this, hold on to it back here and push down on it, you would expect much less deflection. And the reason is because this is the moment of inertia coming into play in a very common kind of experience. Let's calculate the difference in the stiffness in these two orientations. So let's say that this ruler is 1 inch wide, and let's say that it is 1/10 of an inch thick. We're going to calculate the moment of inertia about the centroidal axis, and I'll say that this is equal to BH cubed over 12. The base here is equal to 1 inch. In other words, this is the base, and this is the height, the thickness. So that's going to be 1, and 0.1 cubed over 12, that's equal to 8.33 e to the minus 5th inches to the 4th. Now, that number in and of itself doesn't really mean very much. The units of inches to the 4th doesn't feel like it has much absolute meaning. But what we're going to do is we're going to compare this to the stiffness in this other orientation, and I think there we can understand what the value is a little bit better. So this we're going to say in this orientation is 1 inch. That's going to be the height in this case, and the base here will be 1/10 of an inch. So let's find out the moment of inertia of this one. Again, BH cubed over 12. In this case, the base is 1, and the height, or the base here. Let me do this again. The base here is 1/10, and the height is 1 cubed over 12, and here I get 8.33 e to the minus 3rd inches to the 4th. So if you just look at the values here, this one is 100 times stiffer, 100 times higher when it comes to the moment of inertia, and therefore you would see 1/100th of the deflection for a given force applied. We have talked about the centroids of areas, primarily rectangles and triangles, but let's say we have a rectangle here with a centroid and maybe a triangle over here. Remember, the rectangles are kind of halfway between in both the height and the base. Triangles have the 1/3, 2/3 kind of concept. But if you were to draw a line through that centroid, you define a centroidal axis. And what it means is everything above that line balances by our use of moments with everything below that line. We've talked about moments and how centroids, how we compute the centroid using the principle of moments. And it doesn't really matter what orientation you draw that line. If you were to draw the line through there, everything on this side of the centroidal axis would balance with this sort of thing. So the centroidal axis is a critical concept. It can be in any orientation. In other words, it can be this way, it can be this way, it doesn't really matter. So if you have a composite shape, however, it's a little harder to find that centroidal axis, but we do have some tools here. What we have is a tool called the table method, and we can find a centroidal spot, which would be the centroid of that cross-sectional area. And now we can define a centroidal axis, and what it means is everything above that line has some balance with everything below that line. What we're going to find is that every portion of that shape, well, let me back up and say that in bending, this axis, the centroidal axis, is very critical. That is usually the shape, or that is usually the axis that is critical for analyzing bending and stressing, stresses and deflections in mechanics of materials. If we have a composite structure, this is still the centroidal axis, and everything above this also tends to bend about that axis, and everything below it tends to bend about that axis. What we don't have, though, is a tool to figure out the moment of inertia. We know that the moment of inertia of a rectangle is bh cubed over 12 about its individual centroidal axis. But about this axis, we have to use another tool called the parallel axis theorem. And what it says is that this moment of inertia about any piece, about any other axis, is the moment of inertia about its centroidal axis plus the area of the object times d squared. So this would be the moment of inertia about the individual part plus the area, which would be that, times the distance that you're moving it, which would be from the centroid of that part down to the centroidal axis. If you have a composite structure, then you add them all together using the sum of all of these things. So if we have some shapes that are non-uniform or non-regular, meaning not a triangle or a rectangle, we can use the whole minus wholes technique to find out what the sum of the parts is for a moment of inertia calculation. So in other words, if you happen to have a rectangle with a hole in the middle of it, we could say that it is the whole, bh cubed over 12, minus the hole, the HOLE in the middle. When we do that, we subtract them together, and then we'll get the total. If you happen to have a composite structure that looks like this, it is uniform about the x prime axis. In other words, everything above looks pretty much the same as everything below. It's pretty easy to see the x prime axis, which is the centroidal axis. It's also pretty easy to see that this is already on the x prime axis, whereas these two parts have to be calculated using the parallel axis theorem to be put onto that axis. So all you do is you find the centroid of each part, the distance, then there will be an area, and this will be the distance that you have to move it. This centroid of this part will have, and it'll have that distance that you need to move it. And that will be the sum of, that will be the area, the moment of inertia of the structure is equal to the sum of the moment of inertia of each part plus the area of each part plus the distance that you're moving it, that d squared. So I'll call this d and that one d. If you have a non-uniform structure, meaning, or non-symmetric structure, where here is maybe you have to calculate the x prime axis, you'll move this one from its centroid down to there, we'll call that d1, and the centroid of this one will move up d2. And those will be different here, but again, you just sum them together like this. You'll find the moment of inertia of the composite is equal to the moment of inertia of each piece plus AD squared of each piece.